Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I'm going to talk about doing a time domain seakeeping analysis in the ProteusDS ShipMo3D toolset. So for this, we're going to use one of the sample projects that you can download from the ProteusDS.com website, the generic fishing vessel. Where we start off is you've got to have everything set up all the way up to build ship in the setting up the ship model. So just one note that's kind of handy to know: if you click on View Output after running this, way at the bottom of the file here, you'll see some interesting information on the natural roll period of the ship in that configuration at 0 speed. So it's handy to know there's a natural roll period at 7 seconds, and we're going to pick some sea state conditions around that to just check out some interesting ship motion. So normally at this stage, you can do a really rapid seakeeping analysis with seakeep random. Seakeep random just means it's in an irregular sea state spectrum. So this is already kind of configured here. There's a bunch of different forward speeds to check through, relative wave directions. The peak wave period here is 7 seconds, so on purpose kind of close to the roll natural period just to keep things interesting. And we go save and run that. It only takes 2 seconds or so to run through all those different load cases, and if you plot the motion RMS, of course we see, as expected for this kind of system, monohull, peak roll at beam conditions, add some forward speed that it changes things a little bit, but generally that's what we're expecting. And what we're going to do is investigate a bow quartering condition. So not head waves, maybe 30 degrees off. So 180 degrees is head waves, 30 degrees off or so, and we're starting to get some roll motion, RMS roll motion of 5 degrees. And what does that look like in the time domain? There's lots of good reasons to look at stuff in the time domain because it's the underlying assumptions in frequency domain. It can give you some insight about what's happening. So to do a time domain seakeeping analysis, you need to use the FreeMo application is generally for maneuvering analysis, but you can have a seaway in it. The first thing you're going to need to do is let's see here. I think we've already got, and I've been playing around with it. I think we already have a seaway added here. Well, let's just make a brand new one. Let's go add new data, BuildSeaway. And what we're going to do is, this is an individual sea state that we're setting up. And what I want to do is use a spreading function with short crested waves. So instead of unispectrum, we pick a cos spectrum. It's got a cosine spreading function. You can change some parameters on, the range of frequencies and so on. I do want to have the peak period at 7 seconds just to kind of get close to that roll natural period. And I'm going to pick 30 degrees off from 0. So that's the from, where the waves are coming from. And 90 degrees the maximum angle for short crested waves. And we'll run that. So it's generated the input file for that. We can plot the seaway if you like to just get a view of what visual representation if you like. The next step is now we're going to set up a FreeMo analysis here. So again, this is the time domain analysis. What we're going to do is pick our ship motion model file. This is what the output from build ship. So we select that. We want to make sure we has seaway selected, and there's our seaway file that we want. Of course, you don't have to have a seaway. If you don't have this on, it's just in calm conditions, which is obviously ideal for doing turning circles or zigzag tests and so on. We are going to have the ship go straight to a 0 degree heading. It might be nice to have some initial speed. And now we need to set some maneuvering inputs here. So, we can run it for an hour of time. Is going to give us lots of information. Basically, set propeller RPM. You can get some guidance on what that corresponds to. There is a way to do speed control, but sometimes it's just really nice to set an RPM and let it go. When you're in build ship, note the output of build ship here. You can see it in the output if you just click run and do some it'll do an evaluation depending on the speeds that you want. So you can see for 5 knots, you know, it's 72 RPM. It might be going a little bit faster than 5 knots in those conditions. Anyway, so we've got 125 RPM. Initial RPM is always also good, but you know, once you've got it in the maneuver command, all is well. Add another maneuver here. I'll edit this. We don't want an elapsed time. We want set rudder heading, and we want to be going 0 degrees. So I want to change that. And that's it. So now we just hit save and run. And time domain analysis is more time consuming, certainly, than the frequency domain seakeeping analysis. So this will take a few minutes to process. We're using the linear hydrodynamics, so I would expect something like this to take a couple minutes overall to run. So you can see it's churning through the numbers there. All right, and you can see we've completed the analysis here. So it's handy to plot the trajectory of the ship. This is sort of a top-down view, seeing how things are going. So it's starting at the origin and going straight up. That's what we want. Let's plot some of the displacements here. So now we're seeing some interesting information on the time series of heave. If you click, you can see some of the maximums there as well on different points on the plot, and some interesting information on roll as well. It's good to keep an eye on other parameters as well. Plot rudder prop shows some feedback on what the rudder is doing, and the propeller as well. So rudder angle, you know, we're well within the maximum range of values as the system is moving through. So, and of course, you can view the output file. It is a text file, so you can open it in your favorite text editor and process the data as you like as well. So mainly I just wanted to show the process for doing a time domain seakeeping analysis in the ProteusDS ShipMo3D toolset. And we covered that, so thanks for watching.